Howdy. This video is on the relationship between structural chemistry and acid strength. Acids are important compounds and you should be able to determine why some acids are stronger than others. And so after watching this video, you should be able to identify how Bronsted acids and bases react. You should be able to identify the characteristics that make a good Bronsted acid. You should put a list of acids in order of increasing strength based on their structural chemistry. You should be able to identify how Lewis acids and bases react. And you should be able to identify if something is behaving like a Bronsted acid, Lewis acid, Bronsted base, or Lewis base. And so strength of Bronsted acid comes down to three things. And so if we think about it, a Bronsted acid donates a hydrogen ion. And so the HX bond is going to break and release a hydrogen ion. And so the more polar the HX bond, the stronger the acid. The weaker the HX bond, the stronger the acid. And the more stable the conjugate base, the stronger the acid. And so when releases a hydrogen ion, you form a conjugate base. The more stable the products, the farther to the right the equilibrium will go. And so based on these three ideas, we can actually get a good idea of what makes a strong Bronsted acid and what makes a weak Bronsted acid. And so the more polar the HX bond, the stronger the acid. And so this is a row on the periodic table. You have carbon, nitrogen, oxygen, fluorine. The polarity of the bond just depends on the difference electronegativity. And so as you increase that difference electronegativity, you increase the more polar bond. And so HF has the most polar bond. And so it's the strongest acid of these four. Now it's kind of interesting, if you notice the NH3 is actually a stronger acid than the CH4, but a compound could be a stronger acid and could be a stronger base than another compound. There's no reason that can't happen. And so here we have an order of increasing acid strength. Remember, the stronger the acid, the weaker the conjugate base. And so of these conjugate bases, obviously F- is going to be the weakest, and then the CH3- is going to be the strongest of those. And so the more polar the bond, the stronger the acid. The weaker the bond, the stronger the acid. And so remember, on the periodic table, as you go down the periodic table, the atoms get bigger and the bonds get weaker. And so iodine is below bromine, which is below chlorine, which is below fluorine. And so iodine is the biggest, and that's going to give you the weakest bond. And the weakest bond gives you the strongest acid. The weaker the bond, the stronger the acid. HF, you have the strongest bond of these four, and so that's going to be the weakest acid of those four. Now if we look again at the conjugate bases, and so HI is the strongest acid, and so I- will be the weakest conjugate base. HF is the weakest acid of those four, and so F- will be the strongest conjugate base. And so if we combine the two rows of the periodic table, carbon, nitrogen, oxygen, fluorine, silicon, and phosphorus, sulfur, chlorine, and so as you go from left to right, you're going to more polar bond, and so you're going to stronger acids. And as you go down, you're going to weaker bonds. And so of these 8, HCl is actually the only strong acid. And so the more polar the bond, the stronger the acid. The weaker the bond, the stronger the acid. Now we can look at oxoacids. And for oxoacids, you have elements surrounded by oxygen. And then the hydrogen bound to those oxygen are the acidic hydrogen. And so for oxoacids, the greater the number of oxygen attached to the center atom, the greater the oxidation number of the center atom, and typically the stronger the acid. And so again, the way of thinking about it is if you got chlorine surrounded by 4 oxygen, and again, the hydrogen will be on one of those oxygen, the oxygen is more electronegative. The chlorine is going, in this case, is going to have a +7 oxidation state. So that's going to grab electron density away from the OH bond, making it weaker. Now here we have 1 oxygen, and so oxidation state for the chlorine is a +1. And so the OH bond is actually going to be a little bit stronger. And so again, if you have the same center atom, the more oxygen, the stronger the acid. And so we have nitrogen, same center atom, more oxygen, stronger the acid. So nitric acid is a strong acid. Nitrous acid is a weak acid. Sulfuric acid, strong acid. Sulfurous acid is a weak acid. But again, you can only compare the number of oxygen if you have the same center atom. And so the more electronegative the center atom, Again, it's going to weaken that OH bond because, again, you're going to have chlorine, oxygen, then the hydrogen is bound to the oxygen. And so the more electronegative the center atom, it's going to grab some of that electron density away from the OH. So the weaker the bond, the stronger the acid. And so hypochlorous acid, the chlorine has an electronegativity of 3.2, giving it a Ka of 4 times 10 to the minus 8th. Hydroiodous acid, electronegativity of the iodine is 2.7, and so that makes it a weaker acid. Now we can actually think about this the same way we think about small highly charged metal ions forming an acid. And so for a small highly charged metal ion, it's going to be surrounded by oxygen part of the water molecule. And then again, the more highly charged that ion is, it's going to actually start to weaken that OH bond. And so that's how you get acidic solutions from small highly charged metal ions. Now it's the same with the oxoacids. We saw that the more electronegative the center atom, it can actually weaken this bond, making it a stronger acid. And so for iron 3+, it actually has a Ka of 3.5 times 10 to the minus 3. Chromium 2+ will give you 1.3 times 10 to the minus 4. And then you go copper +2, 3.2 times 10 to the minus 8. And so small highly charged metal ions give you acidic solutions. And again, you can also think about the same effect when you're looking at the oxoacids. Now I mentioned the more stable the conjugate base, the stronger the acid. Notice that a lot of acids have polyatomic ions as their conjugate base. And typically these have resonance structures. Resonance structures means they're a little bit more stable. And so when the conjugate base is more stable, that makes the acid a little bit stronger. And so here we have the nitrate ion. It's got 3 resonance structures, and so that's going to be relatively stable. Carboxylic acids are organic acids that are weak acids. They have the COOH group. And so here we got the carbon, the 2 oxygen, and the hydrogen. And so it's a little confusing. It's often written in order COOH, but actually both oxygens are bound to that carbon. Now, if you lose that hydrogen, then you get this, and you're going to have 2 resonance structures. You can have the double bond here, or you can have the double bond there. And so again, the more stable the conjugate base, the stronger the acid. And so one reason carboxylic acids are acidic is because their conjugate bases are a little bit more stable. The second oxygen also weakens that OH bond, which makes the carboxylic acids acidic. And so 2 reasons for carboxylic acids to be acidic. And so again, for the conjugate base, you can put the double bond here, or you can put the double bond there. That's kind of interesting. If you start adding chlorine here, which is fairly electronegative, it's, I think, the 3rd most electronegative element, these chlorine can actually start to weaken that OH bond. Even though you're looking at 1, 2, 3, 4 bonds away, adding a chlorine will weaken the OH bond. And so for acetic acid, you have a Ka of 1.8 times 10 to the minus 5. You make one of these chlorines, and your Ka increases to 1.4 times 10 to the minus 3. Make 2 of these chlorines, it goes to 3.2 times 10 to the minus 2. And if you make all 3 of these chlorines, then it actually goes to 2 times 10 to the minus 1. So why is HF a weak acid and not a strong acid? I mean, if you look down the group of the halogens, HCl, HI, HBr, they're all strong acids. HF is a weak acid because the HF bond is too strong. Remember, the weaker the bond, the stronger the acid. The HF bond is just too strong for it to be a strong acid. Put the following in order of increasing acidity. And so we have hydrochloric acid, hypochlorous acid, and chlorous acid. And so this one, hopefully you recognize as a strong acid. And so that's going to be the strongest one. You should also be able to go from the name to the formula. So hydrochloric acid, HCl, hypochlorous, HClO, chlorous is HClO2. And so the hydrochloric is the only strong acid, so it's going to be the strongest acid. Now, the more oxygen, if the center atom is the same, the stronger the acid. And so the chlorous acid will be the next one, and the hypochlorous would be the last one. Put the following in order of decreasing strength of the base. And so remember, the stronger the acid, the weaker its conjugate base. And so HCl is a strong acid, so Cl minus will be the weak. And then ClO minus will be the strongest base. So HCl was the strongest acid. Of these three, Cl minus will be the weakest base. HClO was the weakest acid. And so of these three, ClO minus will be the strongest base. Why is acetic acid stronger acid than ethanol? And so again, for acetic acid, you got the second oxygen. It's able to grab electron density away from the OH bond, weakening it. And the conjugate base, it has resonance structures, making it a little bit more stable. So when you're looking at Bronsted acids, it comes down to basically three things. The more polar the HX bond, the stronger the acid. The weaker the HX bond, the stronger the acid. And the more stable the conjugate base, the stronger the acid. And again, you can also apply these ideas to oxoacids. And you saw that the more oxygen, the stronger the acid, and the more electronegative the center atom, the stronger the acid. And so we've talked about three acid-base theories. And so we just talked about how to determine relative strength of Bronsted acids. Now remember, Lewis acids are consistent with Bronsted acids. All Bronsted acids are Lewis acids, but not all Lewis acids are Bronsted acids because Lewis theory is more general. And for Lewis theory, you're looking at pairs of electrons. And so it's kind of interesting. Here we have the reaction of ammonia reacting with water. And we can think about it in terms of Bronsted-Lowry theory. And so in this case, the ammonia is going to accept a hydrogen ion, making it a Bronsted base. And the water is going to donate a hydrogen ion, making a Bronsted acid.
Ammonia is a base in the Bronsted sense because it acts as a proton acceptor. For example, it accepts a proton from a water molecule to form the ammonium ion and hydroxide ion.
But we can also look at the same exact reaction and think about it in terms of Lewis theory. And so we'd say that ammonia was a Lewis base because it's donating electron pair. And the water's a Lewis acid because it's accepting the electron pair.
In the Lewis acid-base theory, the emphasis is on the electron pair. Ammonia is a base because it acts as an electron pair donor toward the proton. The proton is an acid because it acts as an electron pair acceptor.
And so when I say the two are consistent, all Bronsted bases are Lewis bases. But again, Lewis is more general, so not all Lewis bases are Bronsted bases.
Lewis acid-base theory is more general than Bronsted theory because it applies to systems that do not involve protons. For example, ammonia acts as an electron pair donor toward boron trifluoride, a molecule that has a vacant 2p orbital.
And so there is no transfer of hydrogen ions in that reaction, but still a Lewis acid-base reaction because the ammonia is donating electron pair and the boron trifluoride is accepting that electron pair. And so you can describe it using Lewis theory. You cannot describe it using Bronsted-Lowry theory. So we can look at this one too. We have ammonia is going to be donating electron pair, behaving like a Lewis base. The metal ion is going to be accepting electron pair, behaving like a Lewis acid. We still consider it acid-base reaction even though there are no hydrogen ions being transferred.
Ammonia also acts as a Lewis base toward metal ions, as in this example of the cobalt-3 hexamine complex. The ammonia electron pairs are donated into vacant metal orbitals.
And so again, Lewis theory is more general. And so the combination of a metal ion, the metal ions behaving like a Lewis acid, accepting electron pair, and a Lewis base can give you these complex ions. So you have metal ion in the middle, and then you have what's referred to as these ligands. And so the ligand has to just be able to donate a pair of electrons. And so heme has an iron in the center, and it can combine with oxygen or carbon monoxide. And again, this is a Lewis acid-base reaction, even though you do not have any transfer of hydrogen ions.
Oxygen binds weakly to the iron ion at the center of a heme group in the hemoglobin molecule. In an oxygen-poor area of the body, the O2 is easily removed. Carbon monoxide, in contrast, binds very tightly to the iron and is very difficult to remove. The presence of carbon monoxide makes it impossible for the blood to transport oxygen effectively.
And so the carbon monoxide is a stronger Lewis base, and so it will bind preferentially to the heme group over the oxygen. And so in the following reactions is ammonia behaving like Bronsted acid, Bronsted base, Lewis acid, or Lewis base. And so if we look at the first one, we see we have ammonia, a copper ion, and then we're forming that metal complex. Notice there is no transfer of hydrogen ions, and so we can't use Bronsted theory. But ammonia is going to donate its electron pair to form a bond with the copper, and so the ammonia is behaving like a Lewis base. Now if we look at this one, we see again we have ammonia. It's got that lone pair. It'll use the lone pair to rip off the hydrogen, and so it's behaving like a Lewis base. It's also accepting a hydrogen ion, and so it's also behaving like a Bronsted base. And so in the bottom reaction, the ammonia behaves both like a Lewis base and a Bronsted base. And so again, please remember, Bronsted-Lowry theory and Lewis theory, they're consistent. Lewis theory is just a little bit more general, and so all Bronsted bases are Lewis bases, but not all Lewis bases are Bronsted bases. And again, we can use Lewis theory even when there are no hydrogen ions involved. I hope that helps.